Hello, everyone. This is part C of Trigger Review. I hope I will finish, most of the part I wish to cover for the purpose of calculus applications. Recap, right? We have ARD. ARDs are always useful. We have discussed in IA how to do A to D, D to A, right? And whether it's special or not special, those methods in part A will work. And secondly, we discussed the graph, some simple identities, and domain and range. And one of the gaps we're going to fill up is going to be the domain for tangent, cotangent, secant, and cosecant. The other four. If we look at from the definitions perspective, right? If we look at from the definitions perspective, that we know that the domain for sine and cosine are all real numbers because it will never have any risk of zero denominator as R is positive by definition. For tangent, cotangent, secant, cosecant, R is no longer the denominator. We sometimes have X as a denominator in the case of tangent and in the case of secant, right? So you can see tangent and secant actually have the same domain, and cotangent and cosecant have the same domain. So in the case of tangent, right? So let's determine the domain of tangent. Domain of tangent. How do we determine that? Okay. I prepared a picture. Okay. And I'm going to bring it here. In order to determine the domain of tangent, and we first, of course, we need to understand the definition. Definition is that we have a point, right? Any point on the terminal side of angle A other than the origin. So we're going to draw. So I'm going to just draw a blue line. Okay, something we are familiar with. So this will be the red line. Okay, and then we're going to have a blue line, right? We know the red is for X, the blue is for Y. Okay. So here we get this example. Okay, you can draw whatever points. Okay. And here we have the red and we have the blue, right? So how do we find tangent? Tangent is basically blue divided by red. Okay, so tangent equals to y over x. But by the color tone, I'd rather use the color so we can be consistent. And the denominator will be red. Okay, and this will avoid a lot of confusion. Okay, so when we determine the domain, obviously the red cannot be zero. The red cannot be zero. So what are the cases that red will be zero? Red is zero if if red is shrink to zero, then the blue will be overlapping with the y-axis, right? So what are those angles, right? So the case that happens, it would be that when red is zero, the blue will be overlapping with the y-axis in the positive direction or negative direction. So what kind of angle would that be? Well, those angles, if you think about the definition of angle measurement, right? If we know the definition of angle measurement, then we know that when the terminal overlaps with y-axis, and that angle would be measuring from this line, that would be pi over 2, or negative pi over 2, or any odd number multiples of pi over 2. Okay, therefore the domain, okay, that for the angle that cannot be, right, the angle can be any real number but, okay, it cannot be pi over 2, it cannot be negative pi over 2, it cannot be 3 pi over 2, it cannot be negative 3 pi over 2. So this list can keep going on and on forever. So in general, we use, because all of these are odd number multiples of pi over 2. So that representation would be 2k plus 1 multiply pi over 2. Right? You can see this is 3 times pi over 2. Then it would be 5 pi, 5 pi over 2, etc., and k be any integer. So that's the domain for tangent. So k is integer, right? And as a result, you know that secant, the domain for secant is the same, right? Because x cannot be 0. By the same reasoning, so how do we determine the domain for the other two? Okay, so that's how we determine the domain for, say, cotangent. How do we determine the domain for cotangent? Well, cotangent is x over y. Cotangent is x over y. And that's red over blue. Red over blue. So blue cannot be 0. Right? So blue cannot be 0. So what will happen if blue is 0? Right? What will happen when blue is 0? Well, blue is 0 if blue is shrink. Blue is shrink to 0, right? How could blue shrink to 0? When blue is shrink to 0, right? When blue is shrink to 0, the red and the radius will be, imagine that the blue is shrink to 0, right? Then the terminal would be the x-axis or the other direction of x-axis, right? So the angles cannot be, right? The angles cannot be either 0 or pi or 2 pi or 3 pi, etc. So in this case, the angle cannot be, it can be any real number but multiples of pi. Okay, so the domain of cotangent and the domain of cosecant are the same. The domain of tangent and the domain of secant are the same. The other perspective, if you are familiar with that tangent equals to sine over cosine, right? Then cosine cannot be 0, right? Cosine is x over r. So red cannot be coincides with what we did earlier. So cosine A cannot be 0, right? Cosine A cannot be 0. because cosine A is, because cosine is read over R, so we come to the same conclusion. So red cannot be 0. Okay, then we will draw the same conclusion. So if you want to go that route, and you can go that route for cotangent. Okay, as far as the graph goes, I'm not going to cover the details for tangent graph, nor cotangent graph, or secant, nor cosecant. And those graphs can easily be found. And you just know for tangent, there will be a lot of vertical asymptotes, right? So all of these values that A cannot be for tangent would be the vertical asymptote. I can show you a picture of it because it's at our fingertips, right? So I'm going to show you a picture of tangent. Tangent A, right? I'm going to draw the picture. So that's how tangent look like. That's how tangent look like. Okay. So what about those values that tangent cannot take? Say pi over 2 tangent cannot take, right? And that's a vertical asymptote. Okay, so let me draw that vertical asymptote to show you, right? So pi over 2 pi over 2 comma 10. So vertical asymptote, so I'm going to use some color that we don't use very often. Okay, so kind of pink, right? Vertical asymptotes. So we have many such vertical asymptotes, right? Another one would be negative pi over 2. So all the values that A cannot be, and those are the X values that would turn, that would be the vertical asymptote, would be vertical asymptote, okay? The next topics I like to go over is the arcsine, arccosine. Okay, the arcsine, arccosine. I'm going to go by the simple way. Okay, I'm going to go by the simple way. Hopefully that will be sufficient. If we need more discussions, and we will. Okay, so for the arcsine function, arcsine x. Arcsine, as we know, is a function that is a one-to-one, but its inverse is not exactly sine, is a piece of sine. Okay, so from the unit circle perspective, okay, so let me grab a picture. Okay, I'm going to grab this picture. Okay, I'm going to grab this picture. Okay, on this picture, that when we define arcsine, right, it just if sine is from angle to ratio, arcsine is from ratio to angle. Okay, so sine is from angle to ratio. So A it will be the input, right? Is an angle. The sine of A, it produces a ratio. Okay, and that ratio is, of course, is blue over R. Blue over R. Okay, arcsine is a ratio. Okay, ratio X will be the input for arcsine. So it produces angles. But these angles are going to be only between negative pi over 2 to pi over 2. So the quadrant 2, sorry, not this sign, sorry, now the check. Hold on, I'm going to delete that. Crossed out. Quadrant 2 and quadrant 3 are crossed out. And this area is the no-fly zone, which means that you cannot measure angles passing them in either way. Okay, so you can only measure your angles as if you measure a positive angle, you can only measure as far as the positive direction of y-axis. That's it. And in the negative direction, you can only measure up to negative pi over 2. Okay, and in between these ratios, right? All possible ratios for sine would be, the range, right? The range. So we know that the range of sine is between -1 inclusive to +1. And therefore, the domain of the ratio for arcsine, which are these ratios x, will also be between -1 and a +1. So you can see the range of sine is the same as the domain for arcsine. However, the domain for sine is all real numbers, but the range for arcsine is only limited to between negative pi over 2 to pi over 2. So arcsine is only between negative pi over 2 to pi over 2. Okay, so I'm going to give you some corresponding numbers. In our previous example, okay, so when arcsine is considered, we're not going to look at anything. You're not getting any angles that terminates in quadrant 2 nor quadrant 3. But let me set up a table to show you something, okay, right here. We know that sine of pi over 6 equals to 1/2, right? We did that. And arcsine half would be equal to pi over 6. So between the first quadrant and the second quadrant and the fourth quadrant, all these correspondence are set up 1-to-1. Okay. So let me put it. Wait. Okay, just leave it here. Okay, we just increase the number of rows then. We know that sine negative pi over 6. Right, we know negative sine negative pi over 6 is a -1/2, and arcsine -1/2 is our function, right? -1/2 would be equals to negative pi over 6. So this correspondence is 1-on-1. You cannot possibly get anything beyond outside negative pi over 2 to pi over 2. Okay. Another case, right? Remember in the first video we have done and insert a row. In a non-special case, right, we have a sine of a theta. Okay, actually we assume theta equals to arcsine of 4/5. And this means that sine theta is equals to 4/5. Okay? Sine theta equals to 4/5. So that you can see the ratio is between -1 to +1, and the angle, okay, the ratio is between -1 to +1, and the angle is for sure is going to be in the first quadrant, terminates in the first quadrant. All right. So for special and non-special, and this angle, because it's a positive ratio, is actually going to be in the interval between 0 to pi/2, meaning it's going to be in the first quadrant. It's going to be in the first quadrant. Similarly, say if I have another situation, right? If I have another situation that I need to introduce a theta, right, equals to arcsine. Oops. Okay. I'm going to put theta over here. Okay. Theta equals to arcsine -4/5, right? And for sure, I know that sine theta is equal to -4/5, and angle theta will surely be in the fourth quadrant. Will be in the fourth quadrant. Will be from -pi/2 to 2. I'm sorry, to 0 to 0. So these correspondence is true for special, okay? Assuming you have done the work in B, right? So you're getting familiar with those special angles. So for special angles, we have sine of pi/4, right? There are only just so many specials, and that equals to √2/2, right? And then of course, arcsine √2/2 is equals to pi/4. So it's a one-on-one correspondence. So the left column and the right column are one-on-one. Okay, they will your arcsine is not going to be 3 pi/4 because that's the terminal is going to be in a no-flight zone. Okay, so it's just first quadrant and the fourth quadrant. Okay, and keep going on this. If it's a negative, then you got negative, right? So negative pi/4, and this will be negative, and this is arcsine of negative pi/4. That's going to be negative pi/4. Okay. Oh, sorry. I remove the other one. Sorry. Okay. So this piece, for the positive one, we need to keep it, right? So the positive pi/4, and the ratio is that. And last but not least, the other two special ones are pi/3, of course, and also sine pi/2. okay? So sine of pi over 3, okay? That's equal to root 3 over 2, okay? Then arcsine root 3 over 2 is going to be, wait, copy, paste, okay? And that's going to be pi over 3. You can see that arcsine takes the ratio and arccosine, arcsine takes angles. Oops, sorry. Okay, I want to go faster than I make mistakes, so it ended up slower. So these are the commonly used values. Some are non-special and some are special. And last but not least, these are the special angles, which are going to be sine of pi over 2. Sine of pi over 2 equals to 1, right? So of course, arcsine 1 equals to pi over 2. Pi over 2. When you have your terminal is going to be the positive direction of y-axis. And once again, for negative pi over 2, so pretty much these are the values that are commonly used. And a non-special case, by the way, we are dealing with a lot of academic questions, okay? Academic questions. Academic questions means that they're easy to calculate. We just want to know if you understand it. So 3, 4, 5 are typical academic questions, and 5, 12, 13 are typical academic questions. And others are pretty much, it could vary in many different ways, but they are all, manageable. They're all manageable. So that's arcsine, okay? And how does the picture look like, arcsine comparing to, sine? Okay, so I'm going to bring you the picture of sine. The picture of sine. And we're going to plot arcsine. Arcsine x. Okay. So what color do I want it to be? I think it should be green because it gives us the arc, right? Give us the arc. That's the green. It's a little bit hard to see, and I also need to adjust the scale. There we go. It's a little bit too light. Arcsine. Wait, where's my arcsine? Arcsine. Make it thicker. Okay, that's the arcsine. Okay, so it's the inverse function of a piece of sine, right? It's a piece of sine. It's this piece of sine. Okay, it's this piece of sine. All right, next we're going to look at arccosine. Okay, guys, let's come back to look at the arccosine. Arccosine is look like this. Okay, arccosine. Okay, so I'm going to still get this picture here. Okay, so arccosine x. Arccosine, of course, its domain is the range of cosine. Okay, so the angle is any angle is the input for cosine. It produces a ratio, which is the red over R, right? But cosine has a range between -1 to +1. So between -1 to +1, right? And the domain of arccosine, however, is ratio. It's ratio. And the ratio x is between -1 and 1. And of course, x is a ratio. And that ratio is x. Okay? So we got the range of cosine covered. We got the range of cosine covered. However, the range for arccosine is not all real numbers. It's only angles between 0 to pi. 0 to pi. In other words, that quadrant 3 and quadrant 4 will be crossed out. So all the angles we're getting for arccosine, given the ratio, input ratio is between -1 to +1, is between 0 to pi. The first quadrant is for positive ratio. The second quadrant is for negative ratio. Okay, so this interval is for positive ratio, and that interval is for negative ratio. Okay, for sine, the positive ratio in the first quadrant, the negative ratio is in the fourth quadrant, right? So when we measure angles for the answer, right, it's just going to be, you can only measure as low as here, right, overlapping with x-axis, and you can measure all of these angles to pi over 2 all the way up to pi, and you cannot go further. Okay, you cannot go further to the third quadrant nor the fourth quadrant. In other words, arccosine is always greater than or equal to 0. Okay, all right, I hope that's clear. All right, so let me write it down. Arccosine is always between 0 and pi, and never will be negative. And once again, we have a table. Okay? And the commonly used value. Let me clean this up. Okay, commonly used value. Okay, I'm going to insert a table with some rows, right? So say a cosine 0. So this is from the first quadrant, and they'll cross out the third and the fourth, right? So we start from whoops, sorry. Okay, start from cosine 0, right? So because we only have first and second quadrant, so cosine 0 equals to 1, and then we know that arc cosine 1 is equal to 0. That's the relationship. And cosine, we're talking about some special angles, pi over 6, whoops, pi over 6, okay, equals to √3 over 2. And arc cosine pi over √3 over 2 is equal to pi over 6. If you have, if you are familiar with the unit circle, you can use this as a reference. Okay, I'm not saying you cannot use unit circle. Of course you can. You just have to know what you're doing, right? So you just have to know what you're doing. So you put your unit circle right here, that will help. But you also need to understand that you crossed out for arc cosine, you crossed out the quadrant 3 and quadrant 4. Okay, so let's continue. All the red numbers, right? All the red numbers. So then you have a cosine pi over 4, right? Pi over 4. And that equals to root 2 over 2. And your arc cosine root 2 over 2 equals to pi over 4. And then you say, wait a minute, I got it. It's going to be like a sine. No, it's not. Okay? Just wait. So cosine pi over 3 only, you just be patient with me, okay? So going from the first quadrant to the second quadrant, you only look at the red numbers, okay? You look at the red numbers. And this is a pi over 3. This is not the same as sine, okay? Because very soon you will find out. Arc cosine half is, arc cosine half is equals to pi over 3. Pi over 3, okay? And cosine pi over 2 equals 0, right? That's the red number is 0. And arc cosine 0 is equals to pi over 2. Okay? So now, cosine 2 pi over 3, 2 pi over 3 is negative half. Okay? So in the sine case, sine is odd function, right? Arcsine is also odd, but cosine is even. And arc cosine is not, okay? Because arc cosine doesn't take a negative value. It's always positive, okay? So now we got arc cosine of negative half equals to a positive angle, 2 pi over 3. So you can see it's different, okay? And the next one, 3 pi over 4. 3 pi over 4. And that's equals to root 2 over 2, okay? Negative root 2 over 2, sorry. Negative root 2 over 2, that red number, okay? And arc cosine negative root 2 over 2 is equal to a positive angle 3 pi over 4. Okay, two more. Okay, and then 5 pi over 6 cosine. So these are one-on-one correspondence. Okay, you don't have another value for it. So this is a negative root 3 over 2. And arc cosine negative root 3 over 2 is equals to positive 5 pi over 6. So you can see arccosine value, they are all what? Either positive or 0. Okay, so cosine pi equals -1, and arccosine of -1 is equals to pi. Okay, so just to cross these out. And all of these pairs are one-on-one and one-on-one only. Remember, there are one-to-one functions, okay, in the second quadrant, All right. So next, arctangent. Arctangent is the consequence, of course, of necessity, because we use it very often. Okay? So let's look at arctangent. Arctangent. Arctan x. Okay? Arctan, and of course it takes ratios. Oh, sorry. Did I draw the picture for you for arccosine? I have not. Okay, so let me do that. Okay, so here's a cosine. Wait, undo. Oh, gee. No, I didn't cause any trouble. Wait. Oh, no, I don't want to lose that. False. All right, we got to finish, but I lost everything I forgot to save. Okay, don't worry about it. It's been recorded anyway. I just want to show you the arc cosine. Okay, so we saw cosine, so we're pretty familiar with cosine now. So in this cosine picture, I'm going to show you the arc cosine. Of course, you can get it at your fingerprints, and including the tables, it's been recorded. I just have to figure out a time to do it again. Okay, so we're going to use green again because it's arc, right? The output of arc cosine is arc. So I'm going to show you that picture. That's arc cosine. Okay, so that's the green is arccosine, and the original curve I wish to use red because you know the reason, right? Because it's made of red the red, the horizontal, the x. Okay, then we're going to look at arctangent. And we know tangent angles, and the domain is that A cannot be odd number multiples of pi over 2. Okay, so I need to save it. I forgot to save it. Oh no. Close this. Okay, I'm gonna save as Trigonometry Review C. Okay, Trigonometry Review C. Okay. So tangent takes angles, and the angles cannot be any real numbers. It has to be not equals to odd number multiples of pi over 2. Okay, it produces the ratio, and the ratio is blue over red. Blue over red. Okay, so for arctangent, arctangent takes the ratio, okay, and that ratio, and of course, it can be any real number, and arctan take it, sorry, okay, that ratio can be any real number because the range of tangent, the range of tangent is all real numbers. I just show you the picture, which is from negative infinity to positive infinity, or you can just get one on your own. Okay. And the rate, and of course, arctangent produces angles, and the angle is going to be negative between negative pi over 2 to positive pi over 2. Okay, exclusive. Does not include negative pi over 2. Does not include pi over 2. Okay. And so that's the situation. So let's look at the picture of tangent. Right, I drew a tangent curve earlier with the vertical asymptotes, so I'm going to draw that again. Okay, so that's going to be, so we're going to draw that vertical asymptotes. Okay, so negative pi over 2. Just 1 second, it will not take too long. Okay, vertical asymptote, we choose a color that's less used, the pink, and medium broken line. So that's one, right? And there are many more. There are many more. So I'm going to give you another one. So there are lots of vertical asymptotes for tangent. Okay. So we pick, we talk about truncation, and we pick one. Okay. So we pick one slice, which is right in the center between negative pi over 2 to pi over 2, exclusive, and we made that arctan. Okay, so arctan, arctangent x, arctan x. So we're going to draw that picture. So this is arctan. Oops. Okay, so I want them to lie side by side, side by side. Okay. And the view, make some adjustment to the view. And there's the horizontal asymptotes, the horizontal asymptotes for arctan. So that's going to be 1 is negative pi over 2, which is below dash, right? Whoops, I want to have a different color. Make it pink again. Purple. Okay, there should be a little bit different. One is horizontal, one is, vertical. Vertical asymptote, horizontal asymptote. And what are these numbers? Okay, so I'm going to mark these numbers for you. This vertical asymptote is, this piece is x equals to negative pi over 2. And this other vertical asymptote, okay, is x equals to pi over 2. The horizontal asymptote up here, that's y equals to pi over 2. And the bottom one here is y equals to negative pi over 2. So these are the horizontal asymptote, vertical asymptote. Some of the special values we can make table of would be for you can make the table using the special values, and non-special values in very much similar way. Typically, let me make a table here. Okay. Wait. Yeah. So this is fine. So I'm going to remove this. Okay. I'm going to remove this. So clean this up. Okay. So just work on the table. Okay. Say for example, tangents of. Oh, I'm going to give you the unit circle. The unit circle. The rectangular system. Well, I have to redraw it because I lost the other ones, right? That's okay. We will do it. Wait, what's going on? Okay. Let me do this. Y equals 0. So draw the picture. Okay. The view. Okay, we got the view. We got the rectangular system. We make a table about the tan and arctan, right? Then remember the quadrant, the range of arctan is between negative pi over 2 to pi over 2 exclusive, right? So quadrant 2 and quadrant 3 are crossed out. And also, because we do not include the y-axis, right? So we have a forbidden line to touch. We cannot touch that line, okay? So that's going to be this one. Okay, so I'm just going to draw that vertical line. Oh, wait, it should be 0, sorry. It should be 0 there. So it should be a broken line, thicker, and that's a forbidden line. Forbidden line, I'm going to use the purple. Okay, so that's the line. When we measure our angles for the range of arcsine, we cannot touch. We can get as close as possible, but we can never touch. So between negative pi over 2 to pi over 2, we cannot touch that forbidden line. Okay? All right, so we got that. So the ratio of tangent, the common ratios, for example, we're gonna get some correspondence, okay? Pi over 6, that's equals to, you can calculate, equals to sine pi over 6 divided by cosine pi over 6. We'll end up with root 3 over 3, okay? And you can also use a unit circle, okay? I'm going to open my other file to, let's see, do I have this one? No. Oh, I know I lost some stuff. I'm gonna bring my unit circle here with me. Okay, so for those of you who are you know, who studied trigonometry, or you just learned trigonometry, and you know, from our lesson B, you can generate this table, or you know how to use it, right? So quadrant, so on this table, quadrant 2 and quadrant 3 are crossed out. The forbidden line, right? The purple. So we just and the correspondence is because tangent is green, is blue divided by red. So blue divided by red, blue divided by red, right? So for tangent pi over 6 is half divided by √3 over 2. That gave us, you know, whoops. That will give us the tangent ratio. So arctan √3 over 3 is going to equal to pi over 6. That's what the arc function is doing for us. And arctan pi over 4. Okay, arctan pi over 4. And that's going to be equals to 1, right? Because the blue divided by red equals to 1. So arctan 1 equals to pi over 4. Okay, and for these, okay, it's odd, right? So on this line, if I copy this and paste, I just want to get this done quickly. Okay, so if this were negative, you can see it's going to be negative. So that's quite similar to sine, isn't it? As in terms of odd or even. Okay, because you can see all of these are positive ratios, negative ratios. There's it's an odd function again. Okay, tangent is odd, right? Arctangent is odd. Tangent is odd. Arctangent is odd. So this table can be done very quickly. Very quickly. Okay, so this is a negative. So we're gonna get this done. And we're gonna move on to the next topics. Okay, last but not least, special. And on some non-special, right? So the next two, we're going to do pi over 3. That's going to be √3, right? The blue divided by red, right? The blue, √3 over 2 divided by half. And this is going to be √3, right? That's going to be pi over 3. And that's the positive, and the other one is the negative. So this is going to be pretty straightforward. But how about those non-special ones? Okay, how about those non-special ones? So we're going to get there. We're going to get there. Non-special ones. Suppose you have a theta equals to arctan. Wait a second. Oh, never mind. I think I made a terrible mistake. This is a 10. This is a 10, not arctan. I wrote it wrong. Okay, guys? I'm in a rush. I wrote it wrong. Terribly wrong. Okay, these are 10. They take angles, produces ratio, and arctan takes the ratio, produces angles. Okay, I'm sorry. I was terribly wrong. That was terrible. Don't do that. If you do that, I will see it and I will call you out. Okay. And suppose we have a theta, right? Equals to arctan of 10 to 12. Okay, then tangent theta would equals to 12. So that's the relationship. Because arctan can take any ratio. Arctan can take any ratio. Okay, so this ratio x is between negative infinity is the same as the range of the tangent. So this is the domain for arctan, and the range is between negative pi over 2 to pi over 2. So for arctan, the relationship is pretty straightforward. You can take any ratio. You can take any ratio or negative ratio. They all work. So let's move on to the next topic. Okay. The next topic is more or less about what are the identities we should know. What are the identities we should know? For this course, for Calc 1, okay, so I'm going to move back up. Common, useful identities. Useful identities. We had some useful identities. Okay, let me bring up my RA. Okay, in RA we got. Oh wait, did I delete a bunch of things? All right. I probably have lost some files, but okay. So here we go. Okay. So we have some identities. Okay, we didn't lose everything. Okay. So these are the identities that are pretty useful. Of course, we know ARDs are very important. These identities are very useful, but these identities are very straightforward. The next identity is this one. We have proved it, right? So all of these identities are useful. Definition ARD we often use, but there's another identity we can derive from this identity, which is if we divide, right? If we divide on both sides, okay, by the same quantity, cosine squared. So we divide on both sides, the same quantity on both sides. This identity actually is rather useful. So I'm going to make the fonts a little bit bigger. I'm going to save periodically. Okay. With this, after this division, and this is going to be tangent square A plus 1 equals to, and this is a secant square. Secant squared of A. That's another useful identity. Okay, then you say, well, what if I divide, instead of by cosine square A, I divide by sine square A? Well, if you do that, right? If you divide by sine square A, sine square A, then you're going to get a 1 plus cotangent squared of A equals to cosecant square of A. Okay, so these identities are fairly useful. There's some other formula. And I have a formula sheet. I will send it your way, which is, this is the one. Let me see if you can see it. Okay, this is the one. This is the formula sheet I'm going to post for your reference, and I think you might need it in Calc 2. Okay, in here, there are double angle formula, half angle formula, sine, cosine, the sum of angles, difference of angles. And in this chart, right? For example, this table would be rather useful. I'm going to point out in terms of usefulness, okay? Double angle formula are useful for your integration, okay? And these two are useful for Calc 2, for Calc 2. For Calc 1, I'm going to use heart. Okay, so these might be useful for Calc 1. We have used this one already. And the double angle. And I will send it your way. And in this chart, I have also demonstrated how to derive them yourself. So if you are the one that want to derive things by yourself in order to be better at algebra and trigonometry at the same time, in this chart, everything was derived from here. Everything was derived from here. And there's the directions given to you for each path. How to substitute to get the next one, what to do to get the next one, how to do to get the next one. And adding or subtracting these two, you get this one, and then you get this one. And adding, subtracting these two, you get these pair, and then you get the other pair. And how we get from this formula to the double angle for sine, double angle for cosine. I also made videos to show how to derive all of them by yourself. So if you are the one that are interested in this, please let me know, and I'll be happy to share with you. Okay, so now I'm going to conclude this video. Thank you for watching.